Okay. Well, so let me begin by thanking the organizers and Adam for stepping in after a bit of kerfuffle. I mean, I hope that this computer, there's a breadcrumb or something under a key which seems to be loose now, but it seems to, hope it's going to work. Okay, so here's a brief outline. I want to begin by asking the question, what can we say is determinately true or false about a quantum system in a certain quantum state? And then I want to apply that to the Frauchiger-Renner argument, and then draw some moral for Copenhagen-ish interpretations. So, so let's just begin with a couple of comments which are sort of boilerplate. Oddly, nobody has really mentioned non-commutativity or non-Booleanity in this conference, and to me it seems like the core thing. So quantum mechanics replaces the Boolean algebra of two-valued observables of a classical system with a family of what Gleason called intertwined Boolean algebras because they sort of pasted together on common elements. You don't have one Boolean algebra, you really just have a whole bunch. And that's the essential difference between classical and quantum mechanics. And the intertwinement precludes the possibility of embedding the whole thing into a Boolean algebra. And so you can't assign truth values to consistently to the propositions about observable values in all these Boolean algebras, because any assignment of truth values is going to make some propositions true, some false, and some neither true nor false. Now, so in this non-Boolean theory, the probabilities are what von Neumann calls in a paper sui generis, or uniquely given from the start, in the sense that they're sort of geometric features of the geometry of Hilbert space, represented by the angle between rays for pure states. They don't, they just come in as sort of like numbers, but which have that geometric significance. And as I see it, the central problem of quantum mechanics is how should we understand these probabilities? I mean, can we understand them as conditional probabilities? They're not probabilities of stuff happening. Somebody has to do a measurement. So the standard view, here's a statement from Dirac. The expression, I'll just read it, the expression that an observable has a particular value for a particular state is permissible in quantum mechanics in the special case when a measurement of the observable is certain to lead to the particular value so that that state is an eigenstate of the observable. In the general case, we cannot speak of an observable having a value for a particular state, but we can speak of its having an average value, and we can go further and speak of the probability of its having a specified value for the state, meaning, and here's the crucial point, the probability of this specified value being obtained if one makes a measurement of the observable. And that's the way these probabilities, these sui generis probabilities are understood. Okay, this immediately, well, here I just want to repeat this. So what he's saying is an observable has a determinate or definite or sharp value for a system in a given quantum state, if and only if the state's an eigenstate, which amounts to saying that the probabilities assigned 1 by the state are true, and propositions assigned probability 0 by the state are false, and all the other propositions are neither true nor false. Okay, now immediately, I'm just sort of going through some sort of standard stuff to sort of set things up. Immediately, this leads to the measurement problem. I mean, what is a measurement? Propositions that are neither true nor false become true or false. It's a very sort of strange thing, really, in an appropriate measurement. So the probabilities between 0 and 1 change to 0 and 1. Somehow measurement makes that happen. And there's nothing like that in a classical theory. In a classical theory, a Boolean theory, everything is true or false. And what happens with the dynamics is that things that are true now change to false, and some false things change to true. But you don't have this neither true nor false becoming true or false. And somehow measurement is supposed to do this. So von Neumann's solution is the projection postulate, because what's true or false is what's assigned probability. What's true is what's assigned probability 1. What's false is assigned probability 0, and that's not the case in the state you start out with. So now you've made a measurement. Something else is true or false. So von Neumann's proposal is, well, then you project onto a new state in which what you found out is true by measurement is true in that state, has probability 1, and what's false has probability 0. And why did I write? Oh yeah, and so the idea is that the unitary dynamics applies between measurements, and you get a collapse on measurement. Okay, so that's a good reason. Let me just go back to modify this standard proposal about what's true or false that I just indicated with a quote from Dirac. There's also a very similar quote in von Neumann, a very similar statement in von Neumann. So one reason you might want to sort of change the standard prescription for what's true or false in a quantum state is to avoid this problem. Another reason, on the Copenhagen interpretation, there's always one ultimate observer in any application of quantum mechanics. And I want to understand this in a somewhat innocuous sense, just in terms of a remark in a paper by Paris and Zurich. Although quantum theory is universal, it's not closed. Anything can be described by it, but something in any particular description must remain unanalyzed. And we concluded, although quantum mechanics can describe anything, a quantum description can't describe everything, because in any particular description on the Copenhagen interpretation, or Bohr's version, or perhaps actually all versions, it's always relative to some ultimate observer. But for encapsulated measurements, it seems that there's more than one ultimate observer. And then there's the question of, well, how do you get consistency? So perhaps by rethinking this standard proposal for what's true and what's false in a quantum state, one can get some, one can get some further, let's say, insight into what's going on with encapsulated measurements. And finally, just a third point. This is from a paper by Zeilinger with a lot of other people, as he's the last author always. It's an early, I think a 2003 experiment. It's a quantum eraser experiment. You have an entangled, I'll just sort of schematically say what's going on here. You have an entangled state like that. So 2 qubits, and you keep 1 qubit on, in this case, La Palma, and you keep 1 qubit on La Palma. This is the qubit you would keep on La Palma, and the second one goes off to an island quite a distance away, Tenerife. I mean, this experiment is actually done, and I pulled this from the paper. So now in Tenerife, you can measure in the basis 0, 1, in which case this qubit over here is either 0 or 1, and it will then go on one path or the other. There's a polarizing beam splitter, and when it gets here, then there's an equal chance of going to either of these detectors. If you measure in the plus-minus basis, where plus is 0 plus 1 and minus 0 minus 1, then the qubit over here is in a plus or minus state, in which case one says it goes along both paths at the same time, and you get one or other of these detectors firing. Of course, overall, the detectors fire with a 50-50 probability, but the correlations allow you to establish that whatever you do on Tenerife seems to be correlated with what happens over here, which can be revealed by the behavior in the interferometer. So I just mentioned this because perhaps you want to say that, well, when I've made a measurement over here and found 0, then I know something that's true about the qubit over here, but that's not given by the quantum state, because the quantum state just says what's true is what's assigned probability 1 by this state. And you want to say something else over here. So that's another reason why one might want to come up with a different notion of what's determinative in quantum mechanics given a quantum state. So, so it's, I want a more precise notion of what's true and what's false in a quantum state, different from Dirac von Neumann. Now, I hate it when people actually reveal bits of slides, but this is the only slide where I'm doing this just because I think it makes sense here. So just an observation to start with. For any quantum state and a Boolean algebra, just one Boolean algebra, generated by the eigenspaces of, in the Hilbert space of an observable R, the Born probabilities defined by psi for this Boolean algebra for ranges of values of these R values can obviously be represented by a probability measure over the two-valued homomorphisms or truth value assignments on this BR, on this Boolean algebra. You've got one Boolean algebra, the quantum probabilities can clearly be, they're just sort of classical on that Boolean algebra, and they can be represented by measures over truth value assignments or technically two-valued homomorphisms, 1, 0 maps, which preserve the structure. So one might ask, what is the maximal extension, calling it F for information frame? I want to use that terminology. It was suggested by Mike Descal, one of my graduate students. What's the maximal extension of this Boolean algebra in the lattice of subspaces of the Hilbert space on which there exist two-valued homomorphisms? So you can talk about truth and falsity, or there exists a truth value assignment if you like. And there's sufficiently many truth value assignments or two-valued homomorphisms to represent the probabilities defined by the state in terms of a measure over the two-valued homomorphisms on this extension of the Boolean algebra F. So it would be nice if you have that, because that would be a way of talking about truth and falsity given the quantum state and given your starting point, a particular observable. It's an extension. Let me just see. So there's actually a theorem which tells you what that is, which I proved years ago with Rob Clifton. And there was a revised version. Shelley Goldstein got interested in it and actually came up with an idea that led to a much simpler proof, which is published a little later. And if you want to look it up, it's on the archive. And the theorem provides a unique answer to this question, assuming that the structure is invariant under automorphisms of the lattice of subspaces of the Hilbert space that preserve psi and R. You want that, I think, because that's your starting point. I mean, you start with psi and R, so you want some structure which doesn't change if you keep psi and R fixed and you change, you make a rotation or something in Hilbert space which preserves psi and preserves the partition of Hilbert space defined by R. So just to give you a sort of a feel for, I'm not going to prove the theorem, I'm just going to state what it is and then talk about it. But just to sort of give you a feel for the problem, Koch and Specker proved sort of the opposite result. They considered a part of Hilbert space, considered the question of assigning truth values, so to speak, to Hilbert space. And then they came up with 117 bases which are related in a certain way. I mean, in a three-dimensional Hilbert space, so some of the rays in one Boolean algebra are the same as in another one. And as a result of, by considering this structure, they show that there's no way to assign ones and zeros on this structure consistent with the it's a partial Boolean algebra for Koch and Specker, and they showed you can't do this. It's a well-known result. And then there was a whole industry of people trying to come up with smaller structures on which you could generate a Koch and Specker contradiction. And I think in a three-dimensional Hilbert space, the smallest structure is known as, unless there's new ones that I don't know about, have 31 rays. And 31 rays in Hilbert space and various orthogonality relations between them. Quotient and commons, quotient and Conway, I said Conway. Quotient and Conway showed that, and then people started taking like four-dimensional Hilbert space. Adan Cabello had a whole lot of results like that. This is so the game there was what's the smallest structure on which we can generate a Cauchy-Becker contradiction, and this theorem is sort of the opposite. It's what's the biggest structure? I mean, how big can you take Hilbert? Can you take rays in a collection of rays in Hilbert space and assign ones and zeros to them before things sort of blow up? And you start with in order to make the result precise, or the notion precise, we need to start with a particular Boolean algebra and then consider making that bigger.
So that's the biggest set of rays that can be colored consistently?
That's
the kind of
that's the biggest set of rays that can, that's a good way of putting it. What's the biggest set of rays that can be colored consistently, red and green? Starting in this particular way, because, I mean, if you just say, what's the biggest set of rays you can color consistently, it's not well defined, so you need to say, well, there are all sorts of big rays, so big sets, rather. So this is a precise notion. You start off with a Boolean algebra, and you make it bigger and say, well, how big can I make that? Okay. And so that ought to be the kind of structure that you want, because given the state and given a particular, if you like, preferred observable, you get a particular structure. And the structure looks like this. So I think it's pretty much the only picture I've got here. But these were red, but they're now black because this guy doesn't produce red. So there's the quantum state. I'm considering a case where this observable R that I'm starting with, just for simplicity, has two eigenvalues, little r1, little r2, so two eigenspaces. And to generate this structure, I take the state, I project it into each of these subspaces. So these green rays are the projections of psi into these two subspaces. And then there's a whole lot of the Hilbert space left over, namely the subspace which is orthogonal to these two. I mean, if this is a two-dimensional Hilbert space and this is a two-dimensional Hilbert space and the whole space is n dimensions, then this thing here is n minus 4 dimensions. So I take the projection into here, the projection into here, and then I take every ray in this subspace here, and note that the state assigns probably 0 to this whole subspace and to every ray in this subspace. So I'm calling this the null subspace. So these are the generators of this algebraic structure. It's a lattice, a sublattice, or a partial Boolean algebra. A little different, I mean, in terms of if you did constructed the proof. But so it's a sublattice. There, in this particular case, just two two-valued homomorphisms on it. The two-valued homomorphism which assigns true to this, or 1, and 0 to this, and 0 to all these, and the one which assigns true to this, and 0 to this, and 0 to all these. You can't make one of these guys. By the way, just to clear up the diagram, these are orthogonal because these are eigenspaces, so they're orthogonal. And I'm considering every ray in here. Why can't I consider a two-valued homomorphism which assigns 1 to one of these? Well, I can't because, well, if I'm talking about a lattice and I assign 1 to these, then 1 to this one, then seeing that this is 0 and this is 0, I'm going to have to assign 1 to some other one that's some other ray, and so I'm going to get the intersection assigned 1, which is impossible. Or if this is a partial Boolean algebra, say this is partial Boolean algebra. Suppose this is 3 dimensions, and I assign 1 to this guy. Then there are 2 other orthogonal rays in here to make up a Boolean algebra. So I'm going to have to assign 0 to this and 0 to this because it's orthogonal to this. That means I'm going to have to assign 0 to the 2, it's a 3-dimension, remember? I assigned 1 to this. I'm going to have to assign zeros to the 2 orthogonal rays, which means that I'm assigning 1, 1, and 2 zeros to every orthogonal triple in here, and that's impossible if this is 3 dimensions. So, or more. So there are only 2 two-valued homomorphisms in this case. Okay, so that's the structure, and you can think of it as a generalization of, well, let me just first say this. So this is the unique maximal sublattice satisfying the constraints of the theorem, that it contains BR, the starting point. There's sufficiently many two-valued homomorphisms to represent the probabilities defined by psi as measures over these, and it's invariant under lattice automorphisms that preserve psi and R. I'm saying lattice instead of the more general notion of Koshner and Specker, because the proof is the lattice proof. We weren't able to prove it for, it would be more complicated to prove it for partial Boolean algebras. Somebody proved it for, there's a topos theoretic proof of the theorem, so it is quite general. And notice that now probability can be understood, to quote the Dirac quote, as the probability of this specified value being obtained if one makes a measurement of the observable. In other words, once you fix R and you fix psi, then there are certain things that are true or false. What you have are all the possibilities for true or false in this sublattice, and you can understand the probabilities as probabilities that the particular one shows up when you make a measurement, as you can in the Boolean case. Now note also that we no longer have the eigenvalue eigenstate rule. You can't infer from what's true at a particular time to the quantum state, because we have the quantum state, and then we have a whole bunch of things that are possibly true. And these don't get assigned probability 1 or 0, so you can't go back to the quantum state. Also note that this...
Can you expand on that? I didn't quite understand.
Well, if you know, let's go back to this thing. I mean, if this thing, there's the quantum state. Yes. What you know is that this is true, or this is true. But, I mean, if you know that this is true, well, you don't know what the quantum state is. Oh, and notice also that the quantum state is not in this determinate sublattice. So this tells you, the possible truths and falsities. So this could be true, and this false, and all these false. Or this could be true, and this false, and all these false. But this thing here, where you started off, is not in this information frame. We initially called this in the...
But if you give a truth assignment, does it not uniquely determine the quantum state then? Because all the other ones have to be false, and then you know that the quantum state is orthogonal to the...
Well, this quantum state isn't orthogonal to this. It's this is a projection of psi. I could have psi sticking out here, and these are... So the quantum state can't be part of this because it's maximal and it's unique, and the quantum state isn't in it. It's not embeddable into a Boolean algebra. Why isn't it embeddable into a Boolean algebra? It's a sort of generalization of a Boolean algebra in this sense. Well, there aren't sufficiently many two-valued homomorphisms on the structure to separate every pair of distinct elements, which is a necessary and sufficient condition for a Boolean algebra. In the previous case, we just had, 2, and it doesn't separate the elements in the null space. That is, there aren't every single two-valued homomorphism assigns all these elements probability 0. or value 0. The Dirac von Neumann view that what's true and what's false is what's assigned probability 1 and 0 by the state can now be understood as, well, you start with the preferred observable, the identity. If you start with the identity and perform the construction, then you've got the state. You partition the Hilbert space into the eigenspaces of the identity, which is the whole Hilbert space and the null Hilbert space, and then you project into the whole Hilbert space, and you have the same vector, and then you consider everything orthogonal to that, as having probability 0. So this it just generalizes the standard view by saying, well, you could have other observables as your starting point. In this paper I wrote with Rob Clifton, we pointed out that you could have various interpretations depending on your starting point. So you could take R as positioning configuration space, for example, in which case R is your always determinate observable, and then you get Bohm's theory. And we elaborated in detail in the paper how you really get Bohm's theory in this case. Or you could take, I mean, this is no longer popular. People had modal interpretations where what Dennis Deeks, for example, was big on this, and various other people, where you consider the biorthogonal decomposition theorem. You have a quantum state, which is, and you want to sort of make sense of measurement on this theory. So you say, well, you do a biorthogonal decomposition, and then that picks out the determinate observable, the observable, with respect to which you've got this biorthogonal decomposition, and those propositions are true or false. Or you could just consider, and this is sort of a more sort of Copenhagenish view, you could project onto the eigenspaces defined by the pointer readings in a measurement, and that will give you a particular structure, particular information frame. And you could take decoherence, if you like, as selecting the preferred observable. Okay, so now, okay, that's the first bit. So now we have a sort of notion of what's sort of true or false, which is different from the standard notion. And now I want to move on to the Frachinge Renner puzzle or thought experiment. And I want to use, everybody uses different notations, Alice and Bob, and also Yolandi and names like that. I'm going to just sort of stick to the original notation so there's not cause any confusion. So you start off with a state like that. The R refers to this random quantum sort of coin, if you like, where you get heads or tails, and S is the system, and with 1/3 probability, the first friend prepares, if the friend gets heads, prepares the state down, and if not, then this state, a linear superposition of up or down. So now, the story goes like this, and again, I'm just using exactly the same notation as in the paper. At time 0 on the nth run, F bar measures H and T and prepares these states, and then the overall state is this. The L bar refers to F bar, bar's lab, and this refers to the state of the whole laboratory associated with F bar getting a heads outcome. And similarly, this state here refers to the whole laboratory where F bar gets a tails outcome, and that's correlated with the down state of the system and the state of the system here. A little later, F comes in and measures the spin, and that changes the state to this state where the L bar and the L refer to the states of the whole laboratory. So now this is 1/√3 times this whole, their it's a little difficult to sort of read because of all the pluses and whatnot, but this is a product state in which you've got heads and minus for the whole laboratory, a product state in which you've got tails and plus, and tails and minus. Or you could think of this as tails, superposition of plus and minus. And this state over here is exactly this state over here, just rewritten in terms of the OK fail basis. They're exactly the same states. No transformation has occurred. It's a state before W bar measures at n equals 20. W bar measures OK fail, and so I've written it so that measures OK fail on F bar's laboratory, L bar. So I've written it in terms of the OK fail states of L bar, and these are still the plus half and minus half states of L. Again, if there's an L here, it's the state of the whole laboratory. Okay, everybody's familiar with this, but I just wanted to remind everybody of this notation. Now, so what are the non-null generators of this structure in these cases? If you take the preferred observable as just the pointer readings, if you like, of the measurers. So in this case, F bar measures heads or tails, prepares the state. And so I've written here, just to emphasize, I've written E subscript this, because what it is just, in this particular case, it's just going to be this information frame is going to be generated by these two states. But this frame is understood not as states, but as giving you the propositions, the quantum propositions, which are true or false. And so I've written E subscript this. So they're represented in Hilbert space by projection operators. E maybe stands for event. And so you can have this thing being true, or this thing being true, and these are just the positive generators that'll give you the whole structure. The null generators are all the vectors or all the rays in the space orthogonal to these. Then F measures the spin, and you get 3 of these generators, and then W bar measures OK fail, and just going back, you get this and this, which gives you these two propositions. Now the logic of the thought experiment is just this, that if W bar gets OK, then this is true. And so if this is true at n equal 20, then at n equal 10 by an assumption of consistency, but not quite in the same sense as just consistency in the sense that if this is true at this time in this information frame, then because you've got this statement over here is true here, we can infer that this must have been true at n equal 10. And that's in fact what the argument in the paper does do. You go from, well, if W bar sees OK at n equal 20, then at n equal 10, the state of the lab must be that. And so at n 0, 0, you can move to that. I mean, you don't go from here. You infer that must have been the case. In fact, these another way to think about it is that these sublattices have this and this in common here, and this in common here, and so we link those in terms of truth, on the basis now of some kind of assumption of consistency, which seems reasonable, and which I haven't put down formally. But now notice that you end up with this particular statement here, that the lab L bar is in a state corresponding to F bar having observed tails, and this proposition is true about S, the system that has been prepared. Now, I say consistency allows you to go from these various measurement outcomes at the various times to this particular statement. But what's true or false at one time doesn't evolve dynamically to what's true and false at a later time, as in classical mechanics. What's true and false at a later time is determined partly by the quantum state and probabilistically. So this inference that's in the paper seems to me problematic. To infer that after t equal 10, L is in the state this, plus half, plus minus half fail is a claim about the quantum state, because that's what's done in the paper. You infer from the sequence of measurements that L must be in the state fail, and so then if Wigner measures, Wigner will get fail and not okay. This is a claim about the quantum state, and the way in which the inference goes is, given the measurement outcome of F bar in her lab and the associated preparation of S, F bar updates or collapses the state to this. That is, I got T and I prepared this, and so the state of S is this. And as a result of F's subsequent spin measurement, the state of F's lab evolves unitarily to fail. Or more simply, just note, as they do in the paper, that there's zero overlap between the state of the system and the state OK. But this reasoning, either this statement over here or these statements over here, they all invoke the projection postulate, either explicitly or implicitly, that the state of the system S at 0 is this state. But the state of S is never this state. Why? Because, well, it's entangled with the system in this state. I mean, you can say, well, because of what somebody observed, we know that it's this. But this is the overall state at all times. I mean, at t0. And so to put it differently, before the measurements by what I'm going to call the outer observers, Wigner and W bar, the state at t equal 10 is this state over here, which is heads minus half, tails plus half, tails minus half, for the two labs. And that can be expressed in this way, just writing the lab L in the fail OK basis. And so suppose Wigner bar measures not OK fail, but just measures in the heads tails basis of the lab, and Wigner measures in the OK fail basis. The non-null generators of the information frame are then going to be from this previous state here: heads fail, heads OK, tails OK. So that's what I've written here: heads fail, heads tails, and so on. And so one of these is true and the others are false. So the probability that Wigner will get OK given tails for Wigner bar's measurement, right? Wigner bar is measuring at the same time as W, or just prior, doesn't matter, is going to be 0 because, well, these are the only true things. And here you've got tails and fail. You don't have a tails OK, from which it follows by this, but this refers to Wigner getting OK and given conditional of Wigner bar getting tails, and by consistency now in the sense of the paper, that you can say that this probability, Wigner getting OK, given that the friend gets tail, because if Wigner bar in this case, if Wigner bar sort of sees tails, this is on the basis of measuring the whole lab, but if the whole lab is in the tail state, then consistency says that, well, the friend must have seen tails. So this probability is 0. But what if W bar measures in the OK fail basis, but now there's no information frame in which the inference in the paper goes through. There's no information frame in which OK fail is determinate for L bar, that is for Wigner bar's measurement, and H bar, T bar is determinate for L bar, and OK fail is determinate for L, that is for Wigner's measurement. So it isn't possible to reason from OK for Wigner bar, the first Wigner, via tails for L bar to W bar's measurement outcome. Now, to put it differently, after F's measurement, now what is F? F is measuring, okay, let me go back. Well, F is just measuring spin, and W bar is measuring now OK fail. The entangled state can be written this way. That's the that's how you get 1/12 for OK. And I've got here, in this, the only difference between, let's say, where's this state here? The only difference between, well, this state and, where did I end up here? And this state is that I've expressed it in the previous state in the OK fail basis for both L bar and L, and I've considered the unitary transformation which results when Wigner bar measures L bar. So we just have, what happens then is if Wigner bar measures L bar is just that he gets entangled. So you get OK, and OK, and fail, and fail. If you just removed Wigner bar's states, the prior state would be OK, fail, and so on, which is exactly the same as that previous state. So, and this state can be written in this horrible form here, which is actually an equation that Healy writes down in his paper. Well, not exactly this equation, I've sort of, but equivalent to it. So this, I've written here the lab L bar in the state heads tails, and L in fail OK. But now you see that Wigner bar has now gotten all screwed up and is not in the state of fail or OK. And formally, you can now say that the probability of Wigner getting OK, given that the lab is in this, L bar is in the state T, which is the same as friend F bar having seen T, is 1/6. You can just read this off from this because the joint probability of tails OK is 1/12. I've written this in this way so these things are normalized. So you just read off the probability of 1/12. That's for the joint probability, and the joint probability of fail tails is then going to be 5/12. So 5/12 plus 1/12 is a half. So the conditional probability is 1/12 divided by half, which gives you 1/6. And that probability is also in the paper by Bowman and Wolf on the basis of their conditional probability, generalized conditional probability formula, and in Healy. It seems to me, though, that just writing this whole equation down again, that these conditional probabilities refer really to a third super observer who measures L bar in the HT basis, and Wigner measures in the fail OK basis. And if that's the case, then of course, opening a bar's OK fail measurements outcomes are no longer determinately true or false. So, okay, so that concludes the sort of middle part of the talk, which is applying this sublattice idea to this experiment. And now, well, what's the moral, finally, the last part of my talk? What's the moral of encapsulated measurements for the story about what's true and what's false? Well, there could be an ultimate measuring instrument for measurements on the system in the agent's lab. This is really just repeating in a way what Chaslov said, because I agree with that. Maybe it's putting it slightly differently. So there could be an ultimate measurement for measurements on the systems in an agent's lab. I'm going to call those inner measurements, and a different ultimate measuring instrument for measurements by a super observer on the agent's lab, call those outer measurements. And the measurement update rule for an agent yields a collapsed state that applies to further inner measurements on the systems in the agent's lab, understood in the widest possible sense. I don't mean, it could be, it's whatever makes sense as the agent's lab, not to measurements on the agent's lab. And the lab might be entangled with some other systems, and that's relevant to outer measurements on the lab itself and can be known by an agent in the lab. That is the outer state. And that's this latest Bauman and Bruckner paper that Chaslov talked about. So, the outer Wigner can just, in effect, hand the inner agent a piece of paper saying that you're in an entangled state. So I don't see any kind of problem with that, because the agent inside the box is making measurements, updates in the usual way. That updated state will be relevant to measurements in the lab. There's no reason for the agent to think that, my state is, from an outside perspective, is that. Every agent can think, well, for all I know, I'm entangled. I can still do this stuff in the box. So if the agent is told that she's entangled with some other systems, then she says, okay, great, now I know what will happen if you measure my lab, But I don't see any contradiction coming in between the external measurement and the internal measurement, if you keep track of what's true and what's false. So here, just let me sort of end with some Copenhagen-ish remarks. I see quantum mechanics as a new sort of non-representational theory for an indeterministic universe, in which the quantum state's a bookkeeping device for keeping track of probabilities and probabilistic correlations between events that are intrinsically random. And the probabilities are defined with respect to an information frame generated by the pointer readings of what Bohr referred to as an ultimate measuring instrument, which is, quote unquote, kept outside the system subject to quantum mechanical treatment. And the main point, I think, is that non-Booleanity makes quantum mechanics quite unlike any theory we've ever had to deal with before in the entire history of physics. And there's no reason I can see, apart from tradition, to assume that the theory can provide this sort of representational explanation that we're familiar with in a theory that's Boolean. By a representational theory, I mean a theory that says there's stuff out there, particles, waves, whatever. So you have sort of some basic ontology, and you can picture this in some way, because you say in the theory what the properties of these basic structures are, and then you have a dynamics which says how these structures can change and their properties can change. And when you have that story, then you say, okay, now I understand how things are the way they are. There's no reason. That makes sense if the theory is Boolean, because you can talk about truth and falsity in the standard sense, and you don't have propositions that are neither true nor false. So once you have that, it seems to me, there's no reason to think that it's possible to have the same kind of story that you have in a Boolean theory. And I think the Copenhagen interpretation just sort of accepts that. Now, that's not to say that a theory like Bohm's theory might be true. For all I know, Bohm's theory is true. It just seems to me sort of unlikely, but that's just my own opinion, or many worlds might be true. So this claim is not meant to be some kind of like proof of principle that these other interpretations are excluded. I mean, for all I know, they may be true, but this is let's say a position that seems to me to be a perfectly good position that one can take about quantum mechanics. That quantum mechanics is a very different kind of theory that we've had before, and the appropriate way to understand the theory is along these lines. As I say, that doesn't exclude the fact that somebody else might think, well, you could still get a representational account, as in many worlds or in Bohm's theory, but that seems to me has the flavor of something kind of well, like Lorentz's attempt to sort of hold on to a classical space-time in the face of Einstein's relativity theory. So the sui generis quantum probabilities can be understood as quantifying ignorance about the pre-measurement values of observables, as in a Boolean theory, with respect to what I call an information frame defined by the quantum state and a preferred observable. Either a preferred observable which is given once and for all, as in Bohm's theory, or given on the basis of decoherence, if you like, which would be a different determinate observable each time you make a measurement. And the main thing is about this theory is that you have new sorts of non-local probabilistic correlations which are impossible in a Boolean world, and are possible for entangled states where the correlated events are intrinsically random. So the idea is that, look, what non-Booleanity is doing for you is making it possible to have a theory with where things are intrinsically random, not merely random like coin tosses, which you suppose are fundamentally deterministic. And in that theory of intrinsic randomness or indeterminism, we see that we can have new sorts of correlations possible, which are not possible in a Boolean world. And that seems to me the main thing, the main interesting new theory about quantum mechanics as a theory. And in terms of that way of looking at it, it seems to me that a Copenhagen-ish interpretation along the lines that is sort of implicit in this talk is perfectly okay, because it's sort of justified by the fact that this is an entirely unprecedented sort of theory that we've never seen before in the history of physics. So, okay, I'll stop there.
Can you maybe clarify what distinguishes this model from like a psi epistemic theory, where, because here I gather psi represents, as you said, like their ignorance of the true value of some observable, but I gather somehow through this non-Booleanity, this isn't quite the same as these psi epistemic theories that were proposed in the framework of Harrigan and Speckens. Can you clarify that?
Yeah, this is one of these sort of difficult questions which I never know how to answer. I remember once when I gave a talk like this, somebody asked me if I was a Platonist, and then I had to sort of think, well, wait a minute, I mean, how does, there was some kind of claim that something I'd said was sort of suggested that, and I was just got confused and wasn't sure how to answer, because I kept thinking, well, what respect is this sort of Platonist? So, I mean, that's not to answer your question, but just to indicate my sort of puzzlement. So in what respects, maybe I'll just throw the question back to you. What do you see as different in that notion of psi epistemic?
Well, it just struck me that seems to be a strong similarity between your idea of regarding the psi as merely representing ignorance of some underlying true state with respect to some observable, that there's a similarity between that idea and the psi-epistemic interpretations which have been discussed before in the literature, and for which there's a number of results and no-go theorems. And I was kind of wondering, like, is there an element in your interpretation that enables you to avoid those no-go theorems?
Oh, yeah, no, I
think I can answer.
okay, yeah. No, go ahead, yeah. No, I'd like some relief, yeah, that would be very good, yes. Just
So,
like a tag team.
When Rob and company talk about a psi-epistemic, what they call a psi-epistemic theory, they have ignorance of the true value of something, the hidden variable, ontic variable.
Boolean algebra.
And then when they calculate the probabilities for the outcome of a measurement, they write it as the sum over all the values of the ontic variable of the ignorance of the ontic variable times a conditional probability for measurement outcome given the ontic variable. So in other words, they use a standard rule from probability theory for calculating the probabilities, whereas Jeff is in this non-Boolean setting where the probabilities are calculated via Born's rule, as justified by Gleason's theorem.
Exactly.
And there's no way to rewrite that in that way, as a law of total probability. Good. Good, but not good for him, because I was trying to give him relief.
No, I mean, I think the question boils down to, so you have these information frames, and the question is, so once you specify an information frame, you have an ordinary classical probability over the non-null elements of the information frame. And this question just boils down to, so how many of these information frames do you allow somebody to consider at the same time? Because if you say the answer is all of them, then you effectively have a contextual variable theory. If there's some kind of limit on them, as in decoding histories, then it's very similar to like a decoding histories kind of stuff.
Why? We gave the same answer.
Sorry?
I think we just gave the same answer.
No, because I think that if you say it's all of them, then you have an ontological model.
But the only way you get to this way of calculating probabilities that's used in quantum mechanics, if you assume the existence of an ontic variable, is to have a contextual model. So he's treating them as ontic variables. I mean, there is an ontic variable in Jeff's view.
Well,
It's the truth value of one of the propositions in
Yes, but it's not. I mean, because this whole these information frames aren't embeddable into Boolean algebras. I mean, that's. I would say, you know, that it's sort of. See, that's why I'm sort of having difficulty answering the question, and why I've sort of had similar difficulties with sort of Platonism. I'm not sure how to fit this into the framework, because I would say that if the what I would want to say is that if this information frame structure were embeddable in all, you know, in general into Boolean algebras, well, then that clearly would be a hidden variable kind of account, because you would say, well, you know, these probabilities are just representing ignorance really about the ontic stuff that can be represented in this Boolean algebra into which I can embed everything. But given the non-embeddability, I don't, you know, then I don't know quite what to say. Yeah.
So, I mean, one can have maybe, defined joint probability for possible measurements, but they must be contextual. And then the question is, you will have some kind of Boolean algebra for each individual context. Then you ask yourself, what for I need this Boolean algebra? It's just overkilling the whole thing with all these possible joint probabilities, and that put the real question in, even in the program itself.
I think that Jeff outlined several different possibilities. One possibility is, correct, so you have information frames, and how are you going to determine which information frames are relevant, which ones you want to take into account? One possibility that was mentioned was we just use the one decoherence basis. Right? So if you just have that one single frame, then you have a probability distribution over that frame, and knowing the state, knowing the truth valuation in that frame is not enough to determine the probability for any other measurement.
Yeah, exactly.
You then need the quantum state as well. And if you want to say, want to formulate this as an ontological model, then it would be a psiontic ontological model in which you have the quantum state and the truth valuation in this one frame. On the other hand, presumably if you consider enough information frames, if you say, I'm going to have in my model all information frames, then you have enough information just in the frames themselves to determine all the probabilities. In particular, if you have the Dirac-Neumann frame, where the operator is the identity, then you have the quantum state already.
Yeah.
So it all depends on how many frames, how many of the frames you consider as part of your ontology.
Well, I mean, the fact that these frames could be representing truth values which are perspectival, in which case different agents could each have a different frame, and the quantum state is really kind of telling you how to coordinate the distinct kind of perspectival realities of a set of agents.
So you could do that. You could say you're only allowed to consider one frame, but different agents can consider different frames, and then you'll have a perspectival model, I guess.
Yeah, well, I really, in preparing this talk, I went back to this old paper that I wrote with Clifton, partly because what we thought we were doing there was something similar to the Fraukinger-Renner paper, which uses the thought experiment to compare different interpretations of quantum mechanics. In that paper with Rob, we also thought we were doing the same thing, but we just said, with different choices of this preferred observable, you get different interpretations. And I thought it would be interesting to take a look at this new work in terms of that old notion. But in doing so, yes, I'm sort of, I guess I haven't thought it through completely. So this is a workshop, so I propose this sort of as an idea in the workshop. And one could take different stances, as Matt has said, with respect to how this all plays out. And so I guess that what I'm really doing is just sort of throwing out this notion as relevant to the problem that we're considering here. Yes.
Different question. One of your you've got two papers on the archive that I think are in my possession. I have two of your papers with two different titles. I don't know if they're both on the archive. One of them was titled "Why Bohr Was Mostly Right." So, where was he wrong? Where was he right?
I'm trying to remember now that.
I've read the title, but I haven't read your paper.
I haven't read the paper. That was, I think, what I was trying to do was sort of give a sort of a Bohrian story, but sort of in a line, what I was trying to do was to say, look, what Bohr was getting on was sort of on the right track, but and focusing on what he meant by classical. And what I think I said in that paper, if I remember correctly, is that if we take Bohr as meaning Boolean by his use of the word classical, then we get a sort of a different perspective on what he was saying. And now, of course, he never used the word Boolean. He never talked about Boolean algebras, as far as I know. So this may not be, Bohr. And so, in the spirit of sort of Bohr-ish or Copenhagen-ish, I was writing that paper. So, here is a way of making sense of what Bohr is saying by thinking of quantum mechanics as a non-Boolean theory, and taking Bohr as pointing out that in order to apply this theory, we have to always sort of do it with respect to a Boolean framework, and that's a framework sort of set up by the ultimate observer. So and that's necessary, according to Bohr, to make sense of the theory, that everything has to be ultimately sort of referred back in that sense. But the underlying theory is what's going on in the world is non-Boolean, which is why Bohr says you can't picture the quantum world, because that's non-Boolean. And so don't even try, because that's quantum mechanics. But in order to apply the theory, we have to refer to measurements, and the particular measurement context has to be always described in a Boolean way. And the reason we can't extend that as we can classically is just because of the non-commutativity. And it seems to me, now sort of vaguely remembering that paper, is that, quantum mechanics begins for Bohr and Heisenberg with Heisenberg's insight about non-commutativity. And then Schrödinger comes along and says, oh, there's a completely different way of understanding things, it's really a wave. But Bohr always rejected that. He thought the wave mechanics of Schrödinger was a really nice way to perform calculations, which were difficult in Heisenberg's formulation, but ultimately, conceptually, the right way to understand quantum theory was was in terms of Heisenberg's move, that we have a non-commutative theory, and then the question is, so then, if you take non-commutative as non-Boolean, then the question is, well, how do we make sense of a non-Boolean theory? And from there I get to Bohr's notion of Bohr's insistence on classicality as ultimately an insistence on Booleanity.